4, now we want to transition to a specific type of a cash flow. In this type of a cash flow is called a perpetuity, and it has two features to it. One feature is that we are projecting cash flows that are the same amount for each of the year, and notice the ... over here indicating that the cash flow never ends. The cash flow continue until infinity. So it's a stream of equal cash flow. That's one feature that is made at regular intervals. There is no break in these cash flows. They occur at regular intervals and they last forever. So how do we calculate the present value of a perpetuity like this? So the basic idea is that we have to take each cash flow and convert them into their present value, which is what we are doing here. We're taking each cash flow, and by dividing that by 1 plus r to the power n, we are converting them into their present value, and then we are adding these cash flows up. But where do we stop? How long do we continue to do this, and where do we stop? The good answer, the simple answer is that we don't have to stop. We don't have to continue this process because there's a shortcut to this. And the shortcut is that the present value of a perpetuity is the cash flow divided by the rate of interest. This is the simple formula that will get us the present value of the perpetuity. So present value of a perpetuity is C divided by R. And that's all you have to remember. There's no special financial calculator trick that we have to do to calculate present value of perpetuity. We just have to divide C by R. And here is a simple problem that that illustrates it. You want to endow your alma mater, and you want the endowment to have a budget of $30,000 per year forever. And the rate of return for the university is 8%. So how much will you need to donate to endow the party? Of course, you are donating now so that it can earn a cash flow stream of $30,000 per year. So here is your cash flow stream of $30,000 per year, 30,000 into perpetuity, and the present value of that would be 30,000 divided by R. R is 8% or 0.08, which means you have to donate $375,000 today to convert that into a perpetuity of $30,000 per year. Again, a very practical example of the tools that we have in time value of money to apply it in day-to-day contexts. Over here, it's a different problem. You are willing to donate 4 million, and the university earns a 5% return. How much will the endowment receive per year? So your present value is 4 million. This is what we have to calculate, and the interest rate is 5%. So present value is C divided by R, or C is going to be present value times R. Present value is 4 million. I multiply that by an R of 0.05 or 5%. That will give me an endowment of an annual endowment, annual cash flow of $200,000. So we can do it both ways. An annuity is a special case of a perpetuity. It has the same features of a perpetuity, same cash flows, at regular intervals, without any break, but it ends. The cash flow ends at a certain point in time in the future. So the difference between a perpetuity and an annuity is that an annuity ends after some time. So how do we calculate the present value of an annuity? Again, the same thing. We take each cash flow and calculate their present values based on the basic formula that we know, Cn divided by 1 plus R to the power n, and then we add them up. This present value exercise, we can do it in this manner, or we can apply the formula. So take all of those present values and we can convert that into a formula like this, where we take the cash flow, C, same amount each year, divide that by R, and then multiply this by. So you can see over here the formula has essentially two parts to it. This part over here in red, C over R, that's the present value of a annuity. To this, I am multiplying this factor, 1 minus 1 over 1 plus R to the power n. And this factor that I have multiplied, the second part, is essentially my adjustment for the fact that the cash flow does not go on forever. Now, this formula is not as easy to apply as the perpetuity formula, which was just this part, but it's not very difficult. I mean, it can be applied. So one of the ways in which we solve for this is by using the financial calculator. Okay, so let's take a look at this problem over here. You won a state lottery of $30 million. You can take your prize today as 30 payments of $1 million per year, starting today, or 15 million paid today. Which of these two options would you take if the interest rate is 8%? So let's take option A. What does it look like? 30 payments, but starting today, 1 million today, and then 29 more payments of 1 million each. So what's the present value of, so how do I convert this into a present value? Because my second option is 15 million today. So I want to compare the 15 million, which is today, with this stream of $31 million cash flows with $1 million starting today. So what I can do is I can take the present value of that annuity, which is 1 million divided by R times 1 plus R to the power n, times 1 minus 1 over 1 plus R to the power n. If I do this, that is 11.16 million. That comes out to 11.16 million today. I take the 11.16 million, add the $1 million cash flow that I already have today, that gives me 12.16 million. And so that's my one choice. The present value of the annuity is 12.16, and that's part A. In part B, I was getting 15 million in cash today. So of course I would select part B. I would select the second option. But instead of using the formula here, what would obviously be easier if we were able to apply this into the financial calculator. And for this one, the financial calculator is of great help. So we clear everything. Second, clear TVM, clear work, everything is cleared out. I have 1 million as my present value. So 1. And I'm just going to enter that as millions. So I don't have to write out all the zero, just 1. Negative is my present value. What is my R? My R is 8%, so 8 is my IY. How many periods do I have? It's a 30-year cash flow, but since I have the 1 million today, the first million is at time 0. That means I am taking the present value of my 29-year annuity. So now n is 29. I lost this. Okay. Right here, let me see. Okay. Okay. So let me work this out over here. It'll be easier that way. So we have present value as 1 million. Interest rate IY is 8%. N is 29. And now, sorry, present value is not 1 million. This is present value 1. This is not important to us, because that 1 million we are going to keep anyway. So I'm not going to use this. I have over here an annuity. Need to get this thing to work. Okay, so I have over here an annuity of 29 years. So this 1 million does not represent my present value. It represents a steady stream of $1 million payment. So payment, payment, payment. In the financial calculator, we will call this the payment variable. So my payment variable would be 1 million. That can be entered just as a plus. So I go over here, clear everything. Second, clear TVM. 1 is my payment. 29 is my N. 8 is my IY. Now I compute present value. That's 11.15. So compute present value, 11.15. To this I add the present value of 1. My total present value is 12.15. And that's what we have over here. 12.15 or 12.16. So N as 29, IY as 8, payment as 1 million. This is what we are computing. I'm going to skip the Excel formula part of it. I leave this as optional. If you want to learn it, you can learn it on your own. But this is the formula that you can input into your Excel formula sheet, equal to PV, then the rate, the period, the payment, and there is no future value, 0. And you will be able to calculate it using the Excel formulas. But that's optional. Okay. Your parents have made you an offer you can't refuse. They're planning to give you part of their inheritance. They'll pay you $10,000 per year for each of the next 7 years. Or they will give you their 2007 BMW that you can sell for $60,000 guaranteed. You earn 7% annually. Which of these two choices would you choose? So now, to compare this present value to this annuity stream of $10,000, I have to convert the annuity stream into a present value. So I have 10,000 today, and then 10,000 for each of the next 7 years. So you say $10,000 per year for each of the next 7 years, beginning today. That's the key part. That's the beginning today part, gives you this number. If this was not here, then this would not be here. Okay, so since all that is there, that information is there, which says it's beginning today, so that's 10,000, and then 10,000 each year for the next 7 years. So essentially I have to calculate the present value of this. Okay, so over here I clear everything. So what are the variables that I would be entering? I would be entering payment as 10,000. IY is 7%. N is 7. And I will compute present value. So clear everything. 10,000. For the payment, I don't have to change sign. I can just put it as 10,000. 7 is my IY, 7 is N, compute present value. That's 53,892. Again, ignore the negative sign. And to that, I will add the 10,000, which will be 63,892. There is one small problem that I just noticed over here. It says 10,000 per year for each of the next 7 years with the first cash flow beginning today. This timeline is wrong. This should have ended over here. So basically there are 1, 2, 3, 4, 5, 6, 7 total cash flow with the 10,000 over here. So essentially what is happening is that the $10,000, there are 7 $10,000 cash flows with each cash flow being paid at the beginning of the year. So the N over here should be 6. So if you do it that way, then the present value comes out to be 47,665. There's a slight error in the timeline that is noted there. So 47,665 versus the BMW cash flow of 10,000. Again, you see over here, this is wrong. Right. So that's 47,665 plus the 10,000 gives you 57,665. So N is 6, IY is 7, payment is 10,000, 47,665 is present value. What's the future value of the annuity? So future value of the annuity is we take the, remember this was present value of the perpetuity. Then to that we added this factor, we multiplied with this factor to account for the fact that cash flows end at a certain time. Now I want to take the future value of that. To take the future value of this stream of cash flow, I am treating this whole thing, this whole blob, as the present value, and then I simply multiply that by 1 plus r to the power n. And simplifying, doing a little bit algebra and simplifying everything, this comes out to c over r, which is present value of the perpetuity if you remember, and then I'm just multiplying this by 1 plus r to the power n minus 1 factor. Or I could simply use the financial calculator. So at the end of each year until 65, she will save 10,000. Currently she is 35 years old, 10% per year. How much will you have at the end of 65? Very practical problem. If you're thinking about your retirement, you think about at what point in the future you will retire. What's your age today? How much money would you need to comfortably retire? And then between now and then, how much would you have to save per year to get to that point? So it's a very practical problem. So in this case, we have from year 35 to year 65. So year 36, $10,000, 37, $10,000, year 65, $10,000. If you put this into a timeline, essentially you have 30 payments of 10,000 each. Note this thing, there's a common error is to think that there are 29 payments. But you need to avoid this. If you put this into a timeline like this, you will realize there are not 29 payments, but there are actually 30 payments. So your problem is payment is 10,000, IY is 10%, N is 30, and this time you would compute future value. So you go here, clear everything, second, clear TVM, 10,000 is your payment, 10 is your IY, 30 is your N. I'm computing future value. So 1,644,940. Or $1.645 million at the age of 65. 30 of N, 10% IY, 10,000 payment, You don't need to enter this as a negative. You can enter payment just as a positive value. The future value would be 1.65, 1.645 million. So, and this problem actually shows you the power of compounding. You are depositing $10,000 for 30 years. So literally, as cash, you're depositing $300,000 in cash, but that $300,000, which is earning an interest of 10% and being compounded, allows you to grow that to an amount of $1.645 million. So here is an interesting, little bit more complicated problem. Adam is 25 years old. He will save 10,000 in a retirement account until he's 45, at which point he will stop paying into the account, and then he will retire at age 65. If the account grew at 10%, how much would he have saved at the end of 65? A little bit complicated, but can be done. So here are the cash flow. From year 26 to year 45, over a 20-year period, he is saving $10,000. Then all that $10,000, there's no deposit. How much will all of that deposit over the 20-year period, how much would all that grow in year 65? So it looks like a $10,000 annuity for 20 years. Okay, so using this, I can calculate the future value of that annuity at age 45. So all I have done, I've entered N as 20, IY as 10. Again, I don't need to enter that as a negative. 10,000 as my payment. And my future value, this is at age 45. At age 45, I have $572,750 in my account. Now that $572,750 is now going to grow. So 572.50, 572,750. I have 572,750 over here. I leave this in my account, but it is earning an interest over that period. Over the next 20-year period, how much will that grow to? So now this 572.50 becomes my present value, and I'm trying to calculate what my future value would be 20 years from this point forward. So now my N is 20, IY is 10. I enter 572,750 as my present value in year 45, in the 45th year of my life. And then for the next 20 years, it is just growing as a lump sum amount that will grow to $3.8 million, $3.853 million. Pretty good deal. The small amount of investment, or at the end, you end up with a very large sum of money available to you. Okay. The next thing I want to look at is another type of a cash flow that is called a growing perpetuity. So it is a perpetuity like we had before. Remember, in a perpetuity, our timeline was C, 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 and then it grows forever. But now I'm saying this number is not going to be the same. Each year, the cash flows are going to grow at the rate of G. It grows at the rate of 3%. This growth is called the rate of G, or G%. Right? It's growing at a rate of G%. Constant growth. That means the $100 a year from now will grow at 3% to 103. That 103 will grow at 3% to 106.09. That 106.09 will grow at 3% to 109.27. So what's the present value of this perpetuity? But this is called a growing perpetuity. If you remember, the present value of a perpetuity is C over R. Present value of a growing perpetuity is the same thing, C over R, but now I have to subtract the G from here. We don't go over the details on how that equation is developed, but for you it is sufficient to know that that's the formula that prices for us a growing perpetuity. So example over here, you plan to donate money to your university, $30,000 graduation gift, 8% per year. If this is a regular perpetuity, the required donation was $375. But since the cost of maintaining this would grow due to inflation and other factors at the rate of 4%, so that $30,000 is not sufficient. Now, how would you satisfy the request? So if this was no growth, 375. If it is growth, so 30,000, 30,000, 30,000, but now growing at a constant rate of 4%, that same thing would now require an endowment of 750,000. Because it is C divided by R minus G. So that's a growing perpetuity. For a growing annuity, so if you remember, for a growing perpetuity, the formula is C divided by R minus G. And now, if you remember, when we had a growing, when we went from a perpetuity to annuity, our adjustment factor was 1 minus 1 over R to the power n. Now what we have to do, so this was the adjustment that we did when we this was the present value of an annuity. Present value of a growing annuity, the difference is I divide this by R minus G and I add over here 1 plus G. Now this particular formula does not have a financial calculator process to calculate. You have to apply it in the formula method. So here is an example, $10,000 per year, 5% growth, R of 10%, what will be available at year 65. So here is $10,000 as my payment, as my cash flow. This is C, this is R, this is G, 1 plus G divided by 1 plus R. So this is going to be 10,000 divided by 0.05, which is this part. To this, it will be 1 minus 1.05 divided by 1.1 raised to the power 30. So this whole ratio will have to be raised. This whole ratio will have to be raised to the power 30. And then you will take this part and multiply it to this part. And all that gives you 150,463 today. That 150,463 today, in 30 years, I grow it as one lump sum. So 150,463 today, in 30 years, is going to be present value times 1 plus R to the power n. So present value of 153,463, 1 plus R to the power n gives you 2.625 million in 30 years. Okay. Now the last thing we want to look at is something like this over here. Sometimes we have the present value or future value as inputs, but we have to solve for other variables. So for example, over here, you have a 30-year loan. So we know N is 30. Interest rate, so this is N. This is IY. You pay 20% of the purchase as down payment, so you can borrow only $80,000. What will be the annual loan payment? So this borrowing of $80,000, that's your present value. So what's the missing variable? I have to solve for payment. So I can put this into a financial calculator. N is 30, IY is 8. Present value, this time I have to enter that as a negative number, 80,000. There is no future value over here, and this is what we are computing. We are computing payment of 71.6. $7,106. And we can apply this in any context. The interesting thing is that there are 1, 2, 3, 4, 5 possible variables in your financial calculator. If I have any 3 or 4 of them, whichever is my missing variable, I can compute them. So over here, in this case, I had N, I had IY, I had PV. Future value I did not need, is not relevant for this problem. So the missing variable automatically is payment. I highly recommend that you use this as a template. Put this as a template for every problem. Read the problem, substitute the relevant boxes. And whatever box is not filled out is the box that you have to compute. So it's a pretty simple, straightforward process by which you can apply every time value of money problem. Okay, so that pretty much completes chapter 4 for us. The rest of the chapters that gives you several examples. I recommend that you review these examples and try to work them out. And if you have any questions regarding them, you can either see me in my office or ask me during class time.